Thank you for the introduction and thank you for the invitation. In contrary to most speakers before me and due to superstition, I don't want to congratulate the three birthday peoples. Why? The birthdays are on June 15, on June 19, on August 13. And you sum up this birth year, 47, and we have May 2017 minus 1947 gives 70. So, in fact, all three so-called birthday people are 69 years young still. Nevertheless, I want to wish all these three birthday boys a very nice birthday party in 1 month and in 3 months, and I wish them all the best for their 71st coming year of life. So, what about matchstick graphs? A matchstick graph is a planar graph drawn in the plane with straight line edges of unit lengths. And one can puzzle them with matchsticks, placing them on the table, and especially I want to consider regular matchstick graphs, such that at each point k matchsticks come together. And there exists since nearly 30 years this graph, this matchstick graph, and which is called Harborth graph. And I want to tell a little bit on the history, on the personal history, how it came to this denomination, and some further results and problems. So the problem with this graph is 4 regular, no intersections of the matchsticks, and one wants to find the smallest number of points or the smallest number of matchsticks, that here in this case are 52 points and 104 matchsticks for such a regular graph. So you see, we used this graph as a logo of our mail, and in the history, of course, starts as usual with the problem of Paul Erdős. When he visited our university in 1974 and was in the evening in my apartment, he saw a telephone, and the first thing was, can I make a phone call to Ludwig Danzer in Dortmund? And the phone call started, hello, Danzer. And the next sentence was, can you find the minimum number n of k of points in the plane such that each point has distance 1 to exactly k others? So the problem is easy for n equal 2, for degree 1 and degree k equal 2, and k equals 3 gives 6. So the existence of n of k in general is known by the projection of the k-dimensional cube in the plane, so an upper bound is 2 to the k's. However, this upper bound can be improved by these numbers, which follows from this for 3 and for 4 it can be proved 9, and in 1985 I could prove 18 for k equal 5. So in general, the problem is still open, whether this is the best upper bound or this upper bound is straight, or so for 6 distances, 1 to other points, so exactly 6 other points, it is the question open to find 26 or fewer than 26 points such that the construction is easy. You take an equilateral triangle and map them in the distance 1 to another, and in an angle of 60 degrees, the same in another direction gets 9, and so these 2 upper points come up by the so-called Capreca construction. So one day we thought on this problem, and sitting in my office, I saw this at the blackboard and thought, oh, how stupid, so many unit distances intersecting. What is if one takes the following variation to consider only unit edge or matchsticks, which are not allowed to intersect each other, and then ask again to the minimum number of unit edge such that no intersection occur. So for degree 1 and degree 2, it remains the same as before. However, at first there was a certain surprise, since the problem was in a certain sense solved for k larger or equal to 6. The Euler's-Polierian formula says that each planar graph had at least one vertex of degree less than 3, so in a certain sense the problem was solved by non-existence. However, for degrees 3, 4, and 5, it remained interesting. So what about degree 3? Degree 3 was the challenging problem with matchsticks, to find the smallest number of matchsticks such that at each point 3 matchsticks meet, touch, and no intersections occur. So I very often told this to colleagues in conferences, in coffee breaks, or to guests in parties at home, and gave the matchsticks, and most people got this example at first, or this, but never the smallest number, 8 points, or very seldom was found. This is a movable case, and it shows that it is not exactly the problem of Erdős, since here are 2 distances which are always 1, however, however you move this, yes? Since this is a projection of the 3 cube in the plane. So if there are more distances one should use, and they intersect, one can use only 1. Then this is the problem of matchstick graphs. So what is, I said, distances, degrees 3, 4, and 5. Let us first consider the degree 5. I opposed this in 1981 in an open problem in Oberwolfa, and later Art Blockhuis had first ideas for a non-existent proof. However, it was forgotten since there were some gaps, some missing cases, and finally in 2011 Sascha Kurz and Pinchasi together published a proof of non-existence for k equal 5. So, and 5 is infinite. This was published in American Mathematical So it remains the case k equal 4. K equal 4, and there you easily can find this example, the upper example. So this is repeated, and since the angle is 150 degrees, it is just the angle of a regular 12 gun. So this gives you immediately 60 points or 120 matchsticks, which give a matchstick graph of degree 4. However, I tried to get fewer numbers, and playing with matchsticks, I found finally the mentioned Harborth graph with 52 vertices. And this graph is rigid, and in 2011, courts with computer proved the lower bound 34, and it is so far not known whether there exists an example smaller than 52 vertices. So this is open since 40 years now, and the history, how it came to the name, to the denomination. In 1986, there was in Calgary the so-called Strengths Conference on the occasion of the retirement of Richard Guy, who is now 100, as it was mentioned yesterday. And for this reason, the university offered him a whole floor in the library tower for a collection of recreational puzzles and books and so on, which was bought from Strengths from Netherlands. And this conference was also the first occasion where I met, or Ted met me, or I met Ted. And at this conference, I talked about this matchstick graph, and after the conference, several people came and asked me whether they can make a Xerox copy of this graph. So the next week, I went to the IMU conference in Berkeley, and the following week, I had a Fibonacci conference in San Jose, and this was only 1 hour drive to Santa Cruz, where Gerhard Ringel was and lived and taught. And he was preparing his book Pearls in Graph Theory together with his doctoral student Nora Hartsfield. And while we were discussing the chapter Drawing of Graphs, a neighbor, a garden architect, passed by and presented a copy of Science News. And surprise, the Science News is a scientific journal in the United States, and surprise, my graph was on the cover page of this journal. So we discussed, while we discussed this, and so after this surprise, in the book Pearls in Graphs, it appeared 1990 on page 71. The name Harborth's graph was in it, and you see Ringel also used this as an opportunity to the reader to find the smallest example of 8 points. Also other people, Japanese people, made a copy and gave it to the public in Japan to find the smallest graphs, and 2 examples were sent in. The the left one is just the Harborth graph, and the right one is not correct. So you can see, you can do this by matchsticks. However, you can find this by matchsticks. However, you have always to check to arithmetic the geometry, whether it's geometrically really correct with unit distances. This is not the case in the right one. So what is smaller examples are unknown. What is with larger examples? Here are some. This one I mentioned already, the regular 12 gun. This 60 points, 57 points, and these were found by Mike Winkler, an amateur mathematician in Wuppertal or Bochum. So this is nearly the Harborth graph. You can easily construct it in the following way. Leave out this point, and then you put in matchsticks here and here. Then you have the 52-point example. Another example is this with 63 points. And if you shade some of the triangles coming up here, you get this figure, which gives you the impression that you also can cut equilateral congruent triangles from paper or whatsoever and puzzle them on the table to find examples such that each vertex point 2 triangles touch. So we call such packings saturated triangles, so non-overlapping vertex to vertex, 2 at each vertex. And one existing example I showed you, the 42 triangles, and it is also an open problem to find an example with less than 42 triangles. For larger numbers, we could construct such sets for all even t with t at least 42. Odd t's don't exist. We call the handshake lemma. So here are 2 further examples with 48 and with 84 vertices, or 56 triangles and 48 angles, triangles, and they are also matchstick graphs, of course, with 84 vertices. So one other open problem is if you consider these saturated triangle graphs, there are triangles which are triangles and triangles which are not triangles, not shaded triangles. So if you forbid this situation, then it is a question, do such packings of unit triangles exist? And I only could prove that they exist if one allows that 2 triangles in the common vertex, the common vertex is on the side of another triangle, which is possible if you do this puzzling. However, from graph theoretic points, there is a point of degree 6. Then you can find 2 of these ladders and get here a very little smaller angle than 180 degrees and make a large ring from this. The problem whether this packing exists, if this is not allowed, this situation here, then it remains open. I don't think so. Please find an example of unit triangles, vertex to vertex, where no triangle is in between. The only ring graph of this kind, the smallest which I know, has 38,000 triangles. So very large. Triangle sets. So triangle sets are known for two S, T equal 2S triangles, that is for 3T divided by 2 for 3S for vertices. So all multiples of 3 larger than 3 times 21 give matchstick graphs with n larger than 52 vertices. And in between you can construct easy further such examples, deleting these two edges, inserting 1 point, and this has 3s and 3s, then you get this, and 1 times 3s, 3 times s plus 1 gives 6s plus 4, and similar here, deleting those edges, inserting 2 vertices, and the green new unit edges give these 2. So for n at least 126, the matchstick graphs of degree 4 exist, and also for multiples of 3. And so we can prove the following theorem. Every four-regular matchstick graphs exist for all n at least 52, excluded possibly these 7 numbers. So the Mike Winkler found additional cases. So I can show some of them. 67, 65, 64. And you always have to check, they have a computer program to check whether this is geometrically correct. 69, 73, and 74. 2 additional problems may be mentioned. This is a 3 regular matchstick graph without triangles with 30 vertices. However, the smallest example was proved by Kurz and Mazzuoccolo, has 20 vertices. However, this is not that nice. These are not triangles, since there is a small gap here. Yes, so these are a 5-gon, yes? And they proved that 20 is the minimum. However, if there are triangles and quadrilaterals not allowed, then they found an example was 180 points. However, no proof is given that this is the minimum. So, more general, one can ask, what about matchsticks, which will allow matchsticks in a row, in a line? So 1 matchstick or 2 matchsticks, or up to a diameter of 2. So, and then the problem comes up, what is the minimum number of vertices are regular and diameter 2? And if there are examples for all larger n with diameter 2. So for degree 3, we had already the possibility you can use this diamond to get all values. And for multiples of 4 and 4s plus 6, you can insert this piece and also get this. And for 8, we had already this small example. So for d equal 2, we have 6 examples, or for all d larger or equal to 2 and n larger or equal to 6. There is only open one example, what is with 4 points. However, with 4 points, there is only one 3 regular graph. And this can be done with 17 matchsticks as diameter. And this is the smallest possibility to get this matchstick realization. And it is a question whether for which other diameters it is possible to realize, or in general to realize a tetrahedron, plane tetrahedron graph with integer side lengths, integral side lengths. It is known, an old result of HUN-REN from 1945, I think, that if you have a triangle with rational sides, then there is a dense set of points inside with rational distances to all 3 vertices. So if you use the common denominator, then you get many integral examples. However, can you characterize all these so as Pythagorean triangles or yes? So R equals 4. We had already the case of diameter 1, n less than or equal to 52, the smallest, and open 7 cases. For d equal to 2, we can come down from 52 to 18 using this and the mirror image. And if you use d and d minus 1 for d larger or equal to 2, you can also find examples for every d. Here's an example for d equals 3. And another example for d equals 4. And you can find multiples of 6 for d larger than, or every d larger than 4. So for degree 4, it remains the smallest number, that is the 4 regular, that is the octahedron. And here we could prove that the diameter is 13. And so for degree 4 and 13, we have the minimum of 6 points. So in this case, we can come back to the degree 5, since it was proved that n0 of 5, 1 doesn't exist. However, we don't know whether for d equal 2 or 3 and so on, there is existence. I only can show you for 16 points, the second smallest existing 5 regular planar graph, an example of diameter 126, so you need 126 matchsticks in line, or of course the small example, the icosahedron, which is down here, where we need 159. Already in 1987, we used a lot of computer work to find the smallest integral representations of the 5 Platonic planar graphs. So for every planar graph and for every graph in all, you can always ask for the smallest integral representation in the plane, with the smallest means the smallest, largest distance called diameter, which is 7, the blue numbers 1, 1, and 8 for these Platonic solid graphs if intersections are allowed. So in general, one can ask, as I said, for not regular planar graphs, find the problem, find the minimum diameter, as I just said, and this came up to a conjecture only in the 80s of Arnfrid Kemmens and myself. Any planar graph can be drawn in the plane with straight line edge. This is known since Steinitz, since the 19th century, and Wagner and Fari. And now we think not only with straight line edges, but with straight line edges of integer length. So this is open. We could prove 2/3 of a proof, but the largest third remains, and that is missing for a rational 5-gon with rational side lengths. Can you find a point inside which has rational distance to all 5 vertices? This is open. Remain higher dimensions. There, the question is coming up, which is mentioned over there. What is a spatial graph? What is the corresponding thing to planar graphs? Then one could also define a spatial matchstick graph. However, if you consider tetrahedron, unit tetrahedron, then you can easily find such situations. You use the plane cases, make a unit tetrahedron from it, and take the mirror image. Then you have 42 times 2, 84 tetrahedra, unit tetrahedron matching at each vertex 2 tetrahedra meet. However, we could find a smaller example than 84. The smallest we could find so far is this example, the 16 vertex-to-vertex tetrahedra, unit tetrahedra, and we don't know so far whether this is the smallest number we have approved. So much is to do. Thank you for your attention, and nice birthdays next month and in 3 months to Gabor, Ted, and Enver. Thank you.